My goal today is to talk a little bit about what quantum computing is, but really just a little bit, because what I think is much more important is to understand why you should care about quantum computing. Actually, this venue, Exponential Finance, has been talking about quantum computing for a couple of years now, even though quantum computing is only really just starting to tip. But we should probably start this conversation where we start every question, which is really over at Google. Unfortunately, Google gives us some conflicting answers to this one, and there's a number of reasons for that. But I think that the really important thing is to understand that quantum computers are really just a way of being able to harness the computational power that's a little bit more fundamental to the way that the universe works. And we'll talk why that's the case and what that means. To actually answer the question to start off with, I think it's nice going back to 2014. Oh, it looks like Vern is a little bit cut off on his audio there, but essentially, Vern was the former chief technology officer for Goldman Sachs. He is now the chief executive officer for a company called D-Wave, which is actually the first commercial producer of quantum computers. And Vern's point back in 2014 was really that the quantum computers that they are building are a way of trying to harness the computational power that really underlies the physical world. Now, moving forward to 2016, we had Marcos Lopez de Prado, who might be familiar to some of you. He's now the head of quantitative trading, or was the head of quantitative trading at Tudor back in the day. And he was talking about quantum computing as really the holy grail of supercomputing. Most of what he does, we talk here at Singularity University about 10 to the 9, although he really trades 10 to the $10. And he's very interested in looking at ways to be able to connect supercomputing and finance. We'll see. No, well, the nice thing is it says exactly what he's saying up here, but really, he thinks that quantum computers are a way to develop algorithms that can really harness the fundamental laws of nature. And that's exactly in line with my view of what quantum computers are and what they can do. So I think it's a much more singularity type of question to talk a little bit about what's happening with this technology and why we should care. So as a very quick introduction, we're looking at ways to be able to harness this computing power to do things that actually matter in the real world. And we've started out by looking at some of the places where there's the most potential for this technology to be disruptive. And definitely the finance industry is one of those places. We've actually worked with Marcos Lopez de Prado to work and to augment some of the different methods for building portfolios and some of the fundamental things that are possible with computational finance. And in fact, just recently, we saw that JP Morgan has put out a paper. It was a 51-page research paper, which is available to all of you, that goes and shows that actually the traditional way of building portfolios, constructing portfolios with that classic Markowitz method, is done. We should all be now using this hierarchical risk parity method. And the nice thing about this is it's actually very nicely compatible with quantum computers. We've built something that we call quantum hierarchical risk parity. And what you can see is that the traditional portfolio that would have been constructed at a given time, as represented with these orange bars, this just inherently feels a little bit riskier. It's more concentrated, less distributed. However, we can get the same types of returns using this more distributed method. It's just that it's a little more difficult to calculate. But that new computing power is coming online, and it's allowing us, in our own internal reviews, we've seen 20% improvements, basically reduction in risk, while giving you the same types of return. So this is why quantum computing is interesting. And again, we can make all of this information available online. So on our website, you can go and take a look at what this quantum-inspired hierarchical risk parity is really all about. We also do a lot of work looking at how quantum computing will be applied to things like reinforcement learning. But today I want to talk about something else. I'd like to talk about really what it means to do quantum computing. And to help us get down that path, I want to start with something that I think of as a very Singularity University question. It's a question you might have heard about previously, but I think that the idea of are we living in a simulation has been popularized a lot over the last little bit. You might have heard about it from Elon Musk. Elon Musk has been asking this question publicly over the last little bit. He actually read a paper by a guy named Nick Bostrom, who's a philosopher at Oxford University. I assume Nick Bostrom started asking this question after watching The Matrix. But people have actually been asking this question for a long time. And I think the best answer was probably given in the 1600s by Descartes, who basically said it's pretty hard to tell if we're living in a simulation. And I think that that's the correct answer. The reason it's hard to tell if we're living in a simulation is because you can do all sorts of different experiments. You can test the real world in all kinds of ways that you want. But if you are, in fact, living in a simulation, you're doing all of these experiments inside the simulation. And so it's really difficult to kind of get at that point. And unfortunately, I don't have an answer for you here today. But I do want to draw our attention to the fact that if we're inside a computer right now, it's a pretty sweet computer. In fact, if we're not inside a computer right now, it's still a pretty sweet computer. And I think that the really nice takeaway from what I'd like to talk to you about today is that the universe is something like a computer, and we can use it to make money in the finance industry, among many other different things. To give you a sense of what I mean by this, think about something basic and fundamental like a shattering piece of glass. If you wanted to actually take a look at a piece of glass shattering and all the different calculations that happen automatically, this is basically the blink of an eye. When people say like, oh, that happened in the blink of an eye. Well, this is being slowed down to about 300,000 frames per second. And right now, alongside it, we're going to watch the handle of a measuring cup shatter. So this drop is actually still falling. I'm going to show you that one more time, just so you can kind of get a sense of exactly how fast that's happening. Think about all of the different things that had to happen there in order to know exactly how that was going to come together. Now we're going to see this sort of speed back up, and you can watch like what really the speed of the blink of an eye is. But we can understand that actually the blink of an eye is an incredibly long amount of time compared to the universe's ability to either run a simulation or to just do the things that it really does. In fact, there's an incredible amount of information processing happening all around us, all the time, for free. Now, whenever something has happening all around you all the time for free, it's a good idea to harness that to do work. So this bucolic scene is not just a thing of beauty, it's a thing of industry. This windmill uses the power of the wind to mill the grain that you see being grown around here. And so in the same way that we can think about grinding grain with a windmill, we can think about some of these natural computing styles as kind of grinding information with the natural power of the universe. And you might think like, well, that's not really a computer. But I guess it depends on what your definition of a computer is. For example, to me, this is a great computer that can help you do some mathematics. If you spin this first cog a quarter way around, or say a half, then your second cog is going to basically divide that by 2. It's going to, a half turn of the first wheel gives you a quarter turn of the second wheel. And people have actually known that this is a mathematical process for a long, long time. It's the physical realization of an algorithm, and it's using facts about the world to really grind information. This is a place called Antikythera. It's in the Mediterranean, and a while ago, people found at the bottom of the ocean here a device that goes back about 2,000 years. And that device looks like this today, but back in the time when it was actually operational, it was a series of gears, just like what we saw previously. And actually, these gears, if you look at how this was actually put together, they were being used in order to simulate and to understand the movement of the planets and the heavenly bodies. And so, in a way, this is actually a very basic type of a computer. It's not a computer in the way that we think of digital computers today, but yet it's still able to tell us things that are very difficult to know without this technology. And in some sense, it's interesting to think that the universe fundamentally doesn't work on a system of gears, and yet it can still give us information using these gears. But just in the same kind of vein, the universe doesn't actually work on a system of binary bits either. So if you think about our simulations of the world that we've done, this is really my childhood until now, is looking at the way that we've been able to simulate the world for about $200 or $300. This first Mario here was in 1985, and this last Mario is kind of the quality that we're able to do today. This has all really been empowered, this current growth of simulation, by Moore's Law, and I'm sure almost everyone here is familiar with the idea of Moore's Law and the growth that's been happening. But Moore's Law is now dead. We know that the growth in computing power that's happened over the last few years has really been powered not by Moore's Law, but instead by some fancy footwork that's being done by chip makers. And even people like Gordon Moore himself have acknowledged that the thing that's been driving growth historically has now ended. And so people are looking at what's going to come next and what's going to keep things going. I think of this as almost the fundamental Singularity University point, which is that these technology paradigms that have been driving exponential growth have just been sort of interchangeably swapped out. And although each of these technologies has had its own little S-curve where it's plateaued, in general, the process of computing has extended on this exponential curve. So in some ways, you go from a relay to a vacuum tube to a transistor, and you're just doing the same thing. And so what's the big deal? Quantum computers and quantum bits are just the next phase here. But actually, there is something that's a little bit more interesting than that going on, because quantum bits, they're not just a new paradigm for doing the old type of computation. They're a new type of bit that gives you additional features that weren't available in any of these old paradigms. So while this is an evolution of computing, it's also a revolution of computing, and we can talk a little bit about why. We've known since about 1905, maybe a little bit earlier, that the fundamental nature of the universe is this thing called quantum. And what you really need to know about quantum was explained by Niels Bohr. Well, let's see. There we go. And he said that if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. And that's because quantum mechanics really tells us that nothing is solid, everything is energy. The universe works on very different rules than the way that they appear to us. And what we're really trying to do is to harness that fundamental nature of reality that's so counterintuitive to us to process information in a much better way. This isn't a new idea. This is an idea that's been around since at least the early 1980s. In fact, Richard Feynman basically said, well, wait a minute, if the real world is happening in this quantum regime, why are we trying to stuff the real world into a Nintendo and then use the Nintendo to simulate this? Why don't we just build a system that simulates the world directly using that quantum power? And now, that's a little easier to say than it is to do, but people have been working on this really since that time. And now that's starting to become incredibly real. In fact, Google has just announced that by the end of 2017, they're going to be able to do something with a quantum computer that's not possible to do with any classical computer that exists right now. And in fact, we're looking forward to a point when we can do things with quantum computers that you can't do with all the computing resources of the rest of the world. And that's really coming up very, very quickly. And that's because we know that at scale, the things that you can do with quantum computers that you can't do with classical computers or that are very difficult for classical computers happen much, much, much faster. And so what we've been really thinking about at 1QBit, and what I've been spending a lot of my time thinking about, is what things are classical computers really bad at, because we know that those are the things that are about to become possible. If we think about what's really happening in our industry, we know that, I think of a lot of the people who are doing quantum computing as being real visionaries, but the true visionaries are the people who saw what was going to happen with classical machines. In the 1940s and 1950s, we started this process of transitioning these big, clunky machines to the types of devices that we now carry in our pockets, that we have on our desktops, and that process that really started in the 1950s and continues today, that's kind of where we are right now with quantum computers. We're at those big special purpose machines, but we think that that transition isn't going to take 50 years. We think this is going to happen really over the next decade. This is a nice diagram that came from IBM research. And really what they're showing us is that the computing power of the machines that we have available to us right now, which are on the left, these first quantum computers, which are known as quantum annealers, they do some very interesting things, but they're only a kernel of what's going to be possible as we progress from quantum annealers and digital annealers to quantum analog machines, which will be very good at simulation, to universal quantum computers, which will be able to do many different types of calculations. But what's extremely interesting to the finance community is the fact that the things that we know of that are going to be most impacted by quantum computers are actually possible with some of these near-term computers. And so we're actually able to do a lot of this work today. Quantum computers really have this potential to solve problems that would take an incredibly long time with classical machines, and in fact, that may not ever be able to be solvable using a classical machine. And these types of problems, they're not intuitive to think about. It's not something that you're probably saying, I have problems all the time that take me the age of the universe to calculate, but actually, maybe you do. Because very simple problems often explode exponentially in terms of their computational requirements. For example, we've probably got about 250 light switches in this room, and you could think, if we knew that there was the exact right amount of light that we could use to light me on stage right now, you might think about just turning up a dial until we got to that level. But maybe we don't have a dial. Maybe all we have is all the on-off switches, and we want to find what combination of on and off is going to do the best job of getting closest to that. Well, an easy way to find out is you just calculate the light level at each one of the different things, so all off all the way to all on, and that's it. You figure it out, and you sort them, and then you find the one that's closest. Unfortunately, there's more ways to light this room than there are number of atoms in the observable universe. And although that seems crazy counterintuitive, it's just the type of explosion and complexity that happens all the time around you. For example, if you think, all I want to do is build a portfolio of stocks that either has a stock in it or doesn't, well, the S&P 500, if you're just choosing from that, that's the size of the problem that we just talked about squared. This is an incredibly massive number of possibilities, and these problems are around us all the time. The only thing is we've found ways to be able to ignore that complexity and to trade the time that it takes to compute this stuff for approximate answers. And those approximate answers have been the best that we're capable of, but we're now just starting to be capable of much more. So for example, this is a paper that was published, 1QBit in conjunction with the head mathematician at the time of Morgan Stanley, one of the supercomputing experts from Lawrence Berkeley Laboratory, and Marcos Lopez de Prado. This was an opportunity for us to look at ways that we could think of really running the computation that underpins modern finance on these quantum machines. And what we did was we said, instead of looking at building a portfolio just today, and then looking at building that portfolio tomorrow, and then the next day, what if we think about all of the possible options now and into the future as one big optimization problem, where instead of bouncing back and forth to extremes and having all of our profits eaten up by transactional friction, what if we just want to chart a course through all those possibilities to find a way that minimizes transactional frictions? This is something that if we can do, we can save most of these big funds billions of dollars a year, and yet we have now been able to show that there are formulations that are exactly amenable, not to those far distant quantum computers, but to the types of things that we're able to do right now. And so the way that we think about what we're doing at 1QBit is really to connect industry to quantum hardware. Down at the bottom here, we've got a bunch of hardware makers that are starting to understand that quantum really is the future. Fujitsu, Google, Microsoft, IBM, D-Wave, Rigetti, Baidu, Alibaba, Tencent, these companies are all putting a ton of effort into building incredibly complex new quantum computers, and these are all coming out over the next few years. And yet, most of those people, if you go and talk to the technicians and say, why are you building quantum computers? They'll say, because quantum computers are really, really cool. And that's a great motivation, and I absolutely agree, but it's not particularly helpful for people who are in industry who are trying to say, I've heard about quantum computers, but I have no idea exactly how they're going to be connected to what I do. So my goal is to be able to help motivate people to understand that this power is coming. It's something that's going to be available to all of you, and it's something that has real ability to impact what's possible for you to do within your industry and to make money doing all the things that you already do, but in completely new ways. So for example, we've just made a nice announcement of a partnership with Fujitsu where we're going to be building digital annealers, basically devices that are capable of really diving in today to solve some of those problems, to be able to build a platform that you can start building software on top of that will continue to evolve so that your software automatically improves along with the improvements within the quantum computing industry. If you think back to times when you had your 386 and then all of a sudden you moved up to your 486, you can really viscerally understand the slowdown of Moore's law. I remember each year I would get a new computer and I would barely be able to play my old games on my new computer because my new computer was so much faster that I had to actually try and slow it down in order to be able to do the old things that I used to do. Now, I'm using a laptop that's 5 years old and I don't really care when a new one comes out because it's kind of doing the same thing. It's nothing totally new, and it's not exponentially faster than what I used to have available. So if that's the case, we're starting to be in a mindset where we've been conditioned to feel this slowdown of Moore's law, but we need to get out of that mindset because computing power is about to get on an exponential growth curve again. And I think that this is a quote that I first heard at Singularity University, and it's something that really describes where we are today. Although the quantum computing industry, and specifically the software and the tools that are available in order to harness that power, are just a spark. It's just the very, very beginning of what's going to be possible. We know that those sparks are going to turn into a huge explosion, and all of a sudden, you're going to be faced with incredible amounts of computing capabilities that directly tackle the types of problems that are most relevant to what you're doing. And it's going to do this not in 20 years, not in 10 years, but really over the next 3 to 5 years, we're going to start to see this coming online. So my goal today wasn't really to tell you about what a quantum computer is and how a quantum computer works. It's trying to make you believe that quantum computers are going to be relevant to what you do and to encourage you to come and learn more about them. And you can do that out at the breaks. There's a lot of information online, but I think that anyone who ignores the power of these computers does so to your peril, because especially in finance, computing power is really a bit of an arms race. And as you all know, in many of these situations, it's winner takes all. So I would highly encourage you to indulge your curiosity, to learn more, and to find how you can take advantage of this computing power in order to make sure that you're on the right side of that equation. Thank you very much.